Hello everyone. Let's continue with counting. So already we talked about basics related to counting, and today we are going through combination and permutation, and also for the next week and the week after that you will see advanced techniques related to counting. And today also I will mention about binomial theorem beside combination and permutation, and we will talk about them in details. So already we know that counting is important in order to deal with many mathematical problems, which we are using also in our own fields like computer science. The thing is that for the previous session, you saw that we are counting the items, the number of elements, for example, in a set, in a sequence, in function. So now we are talking about the arrangement of those items. So now assume that you have a set, then in the set, order doesn't matter. But when we talk about tuples, then order matters. And the arrangement of the elements inside the tuple, the way we can arrange our items, then we can talk about it and say, for example, in how many ways it is possible. And as you know, for those who had a statistic with me, they know when we talk about probability, first we should know what are the number of possibilities. So first we should know about counting methods in order to deal with such topics. Now let's go through permutation and combination in details. I will give you examples after one. So in permutation, we have now two parameters, n and r. There are two integers from 0, and the maximum number here is n. It means that r should be always less than or equal n. So both of them are positive, both of them are integers, and they can even take 0 as their minimum value. Now here's the formula related to permutation. But what does it mean? I will talk about it as soon as we see also the formula related to combination. Now here, you see the definition is almost the same. We have n as a parameter, again r. So you see the same condition here, but the formula is different. Now it's the time to talk about their exact definition and what's the difference between these two. Let me tell you about it in an example. Assume that we have 10 faculty members, and among them we want to choose dean and vice dean. So we have in total 10 number of faculty members, and I want to select dean and also vice dean for this faculty. Now assume that randomly I select one of them. All of them have the same chance to be selected. So assume that Jack, for example, is selected for the dean randomly, and Jessica is the vice dean. So we may ask, in how many ways is it possible to select 2 faculty members from 10 faculty members, and how we can give them positions like someone should be the dean, someone should be the vice dean. This is one problem. The other problem, which is very similar, is that we have again 10 faculty members. Then I want to randomly give them $100 just to as a motivation for a good work for the whole group. So randomly we are doing it, and assume that the faculty doesn't have that much budget to give us, so randomly the faculty selects 2 faculty members. So $100 will be given to, again, assume that this is Jack randomly happened, but assume that exactly they are the same names here. And $100 again was given to Jessica. So you see, these two problems are very close to each other. Here we are asking in how many ways can we give $100 as a price to 2 faculty members among 10 faculty members. But what's the difference here? The thing is that when I'm choosing my first position as the dean from the faculty members, Jack was selected first. If Jessica was selected first, then Jessica would be the dean of the faculty, not the vice dean. But in this scenario, it doesn't matter whether Jack is selected first or Jessica. Both of them at the end receive $100. So what's the difference here? Here, order matters. When order matters, we call it permutation. So permutation is related to the time when order matters. When order doesn't matter, then this is called combination. So this one is related to permutation, this one related to combination. So we should be careful to use the corresponding formula for each of them. For combination, you can show it like this, or they also use this notation like that. And for permutation, we show it like this. Here, if you compare the formulas together, as you can see here, we have n factorial. Here we have n minus r factorial. Here exactly for combination, we have these terms, but we didn't have this part for the permutation. This one is added because the order doesn't matter. So the number of possibilities here, they are decreasing. Now, please go through all the examples in chapter 6, 6.3 section. It's very important to go through all of them. We will practice together at least with 4 examples in the weekly assignment. But even if I solve 100 examples related to permutation combination, and then when I ask a new question, maybe it sounds new to you. Then how to overcome this problem? This is very similar to mathematical induction. You should practice it yourself. So when I say read all examples of chapter 6, 6.3 section, please do that. It's very important so that you will be ready. And it's better to do it before the weekly assignment so that you can deal with them easier. But anyway, try to solve the weekly assignments, even if we select them from the book yourself before checking the answer in the book. And I will go through them in details, and we will practice this together. But I think the definition is clear. Of course, if you will have any questions, you can ask me at the end of the session. The other thing I want to talk about is related to binomial theorem. I won't ask questions from binomial theorem in the final exam. Usually I do, but for the online exam, this is not a good type of question to ask. That's why this one is eliminated for the final exam. But anyway, this is in your course syllabus, and even during pandemic, I prefer to talk about it. We will use it also in other chapters, so it's good to know about them. So let's go through them together. So what's the binomial theorem? Let x and y to be 2 variables, and let n be non-negative integers. When we talk about non-negative integers, we talk about 0, 1, 2 going to infinity. We don't consider the negative ones. We should be careful about it, because if we are talking about mathematical induction and we say, for example, this proposition is true for all non-negative integers, it means that your first element starts with 0, not 1. Okay. If we talk about natural numbers, then it starts with 1 most of the time. because in some books they also include 0 inside natural numbers. Anyway, now what do we have if we have two variables and n as non-negative integers? The proof is inside your book that this equation is true. It means that when you have the summation of two variables and you power the whole thing, not them separately, the whole thing as a parenthesis to n, then you will have such expression. You can write it as the summation of combination of j from n. So you already know what it means. It means that c, n, j, and it has a formula using factorial. You already know about the formula now. And for x, you power it by n minus j. What is j? J varies from 0 to n. And you remember n was the power here. So we always start it from 0 when we talk about binomial cases. And in statistics, we have binomial distribution, which if you are familiar with that, you know we use the same formula here to find the probabilities of each point. So all of them are based on the same logic. So the summation of them, n minus j as the power of x and j as the power of y. And when you extend it and write everything in terms of the summation, instead of notation, now I extend it. So one by one, you can show it like this. It means that here we are increasing the number one by one, 0, 1, you continue until n. And look at the power of the variables. Here, for x, you start from n, you decrease it one by one until you reach x power 0, which is 1. That's why you don't write it in the last time. Here, it is x power 1. The last one is x power 0. Here, this is y power 0, which is 1. You don't write it. And here, you have y power 1. And you continue until y power n. So this equation holds, and you can see also the proof in the textbook. For pure mathematicians, we talk about the proof, but for computer scientists, it's not necessary anyway. But if you are interested, you can go through the book and find it there. Now, we can ask questions like this if you know about binomial theorem. But as I said in the final for this semester, I'm not going to ask it. So if I ask, for example, x plus y, the whole thing powered by 4, how can I write the expansion? Then you know about the binomial theorem, and you can easily convert it to this. And by using this formula, it's easy to finally reach the answer like that. And as you can see, it's very useful because we used to memorize these things in high school. But now you can come up with your own formula for no matter what's the power. You can write the final answer now easily by using binomial theorem. There are some interesting corollaries related to binomial theorem. I chose this one for you, for example, that let's see what it's saying. And I will also show you the proof. Let n be non-negative integer. Then we have this equation. But how did we reach that? Now assume that instead of 2 power n, I write it as 1 plus 1 power n. What does it mean? It means that I consider x as 1, y as 1, and n is n itself. So I can use binomial theorem here. You see? So instead of x, now I have a number. Instead of y, I have a number. And I can use the binomial theorem to write the formula here. Now that I have values instead of x and y, it's maybe more, it's simpler for us. Like here, 1 power k, I can write the whole thing as 1. Because k is not infinite, it's limited, you see? K varies from 0 to n, so this is limited. It has an upper bound, and it's not infinity here, because if we had 1 power infinity case, as you know from calculus, this one can be vague. But in binomial theorem, fortunately, we are not dealing with such cases. In statistics, you know, for Poisson distribution, this is a different story, and we will talk about it in a statistic course together about it. Anyway, so for both of the cases here, the power has an upper limit, so we know that it's not talking about infinity. So for sure, the final result of these two, 1 multiply 1 is 1, 1 multiply this expression is 1, so this is the final answer, and we prove that 2 power n is equal to this, which is very interesting. We use that a lot. We have also Pascal's identity, which is also very close to what we have learned. And as you can see, we use combination for them. And again, you can find the proof in the book if you are interested. We use Pascal's identity a lot in many courses. And for pure mathematician, it is interesting to ask them how we can prove it. But for computer scientists, I usually don't ask such questions. So what extra readings you can have? You can find more corollaries related to binomial theorem in section 6.4. There are interesting ones and they are very useful for many fields. If you are interested, you can read them. And please go through sections 6.3 and 6.4. Here, these two. Especially this one, because I will ask questions in the final related to 6.3, but it's not bad to read 6.4 anyway, because as I say, it's useful. In the next chapters, we may use them as well. So if you have any questions, please let me know. Otherwise, don't forget about your midterm exam tomorrow at 6 p.m. I will upload it on AutoClass, and you will have 24 hours in order to answer them all and post it on Auto. The level is very easy, and comparing, of course, to a homework exam, and I'm sure if you were comfortable with weekly assignments, it's going to be easy for you anyway. And for those who are having bioinformatics with me, please ask your questions using email. It's not possible to ask it during the online session. But for those who have questions from today's session or any question related to our course for today, please let me know. Yes, exactly. Counting is not included in your midterm exam, and you're going to have it on the